So far we explored heterogeneity in treatment effects by just looking at what variable was the most important for splitting the causal forest. Variable importance showed us that number of priors was by far the most important variable for explaining heterogeneity in treatment effects. So what we do next is that we can actually explore it in a bit more. We want to plot it, okay? So in the end, we want to plot how our treatment effects vary with the number of priors. So in this code, so let me just, and even this one, just let's see what's happening. What we want here is to create a grid, right? If we want to plot number of priors on the x-axis, we want to use only unique values that we see actually in the data set. Remember, number of priors is a continuous variable. I can actually show you that. Yeah, it's a continuous variable, you see, but in fact it's a discrete variable because the number of priors can be just 1, 2, 0, 3, 4, 5, so it's a discrete numeric variable, which then they sort of rescale. As you can see, 0.2108 here. It means that these two people have exactly the same number of priors. We don't know exactly in terms of actual value, but after it's rescaling, those things are still kind of as a step function. So what do? We ask to return us the unique values of this numeric variable. Here we go. This is probably 0 and this is probably 1 prior and so on and so forth. So you see it's not yet sorted out. That's why we put sort. Oh, please sort it out for us. So this is 0, 1, 2, 3, 4 priors, 5, 6, 7 and so on. We can actually return it back to its natural values. What's next? We take this unique vector of unique values for number of priors and we save it to n priors val. Next, we create a new value of X matrix. So what is going on here? Let's take this one. You create a matrix. You populate that matrix with zeros. So what happens if you do matrix 0, 2, 3? It creates a matrix of 2 by 3 and puts values of zeros everywhere. That's what it is. So basically, here you have a matrix of zeros which has as many rows as unique values of number of priors, which is 27. 27 rows. We will create 27 rows and number of columns of X, which is 6. Just picture. Yep, 6. So this code creates a matrix of zeros of length 27 and 6 columns. And we assign it to, and we name it as X test. X matrix for some new manipulations. Then, so we put everywhere zeros and we assign to the first column of this matrix the unique values of number of priors that we have just looked at. Sorry, I should put head X test. So it shows us, or without head, it's just very small matrix. So you see, these are all our unique values of number of priors and the rest is put at 0. So what happens next? So we create a new X matrix for which we will ask our causal forest to predict treatment effects. So it says someone with the characteristics of number of priors equals 0 with whatever what was, like, I don't know, female equals 0, meaning that male, and all the rest is basically 0, not Caucasian, so basically black, and so on. So you create this hypothetical different people for whom the only difference is the difference in number of priors. Okay? So now we actually do the predictions for the artificial test data. We use the function predict. What is our object? Causal forest that we created. New data is X test. Estimate variance equals true. So what does this do? Let's just do it step by step. What does this do? It creates predictions. Outputs the data frame with predictions of treatment effects. It has 27 rows. Why? Because we have we supplied 27 different new data points for which we want to predict treatment effects. So all our different 27 people whose only difference among each other is number of priors. And these are the predictions of treatment effects. So for example, for someone who doesn't have any priors, the job assistance does not affect in any way the wages. If anything, it decreases it. Anyways, predict function takes the causal forest object, takes new data set with some characteristics of people, and then it predicts what would be the treatment effect based on the causal forest that we've grown. Now this is a data frame. Since it's a data frame, we can also look at its, for example, names. It has just two columns, predictions and variance of estimate. But if we wanted to plot it, we also want to have number of priors that we provided. So we mutate it. So we take this data frame piped to created by the predict function. It is piped to mutate function, and mutate function creates a new variable called number of priors, to which should be the same as the first column of the X test. So let's run it. Now we see the head of this new object, causal forest predict. Now we will visualize the heterogeneity. Every time with visualization, let's start with data. What kind of data we put? CF predict. That's what we want to visualize, this object. CF predict. What is our X? What do we want to visualize? We want to visualize predictions. No. On the X-axis, we want to have number of priors. So we put number of priors in X. On the Y-axis, we want the treatment effect predictions. Okay. What does it do next? Geom error bar. Geom error bar creates error bars. So let's just not put yet this part of the code. Let's just switch it off and see what happens if we just do this. As you can see, it plots the predictions of treatment effects as function of number of priors. Now what we want is the confidence intervals around those predictions, right? So geom line creates the line, geom point creates the point, so the point estimate, so it plots those. What we want to add is error bars, and error bars for every single number of priors should be from y minimum, which is prediction itself, minus 1.96 multiplied by the standard deviation of the estimate, which is square root of variance of estimates. So you see, for here, the error bar will be from minus 0.07 minus 1.96 multiplied by the square root of this value. And here. Voila! So now we have plotted the heterogeneity in treatment effects with respect to number of priors, conditional on all other variables are equal to 0. So what does this graph say? The program is more beneficial for people with fewer priors or with more priors? For people with more priors. The higher number of priors, the more beneficial this program is. Now, we sort of see that there is like this kind of effect. What we are not sure and actually looks suspicious is that then the treatment effect doesn't change at all, which can be truth or can be not truth. So what we want to see is how does number of priors look. This is the density. So most of the ex offenders are having very few priors. And there is a long right tail. So those people who have really lots of priors are not that numerous. So that's one of the things where this generalized random forest is lying to us, and you can see clearly it says it's very certain that the treatment effect is around here. There are very few people who are in this range of priors. So the little secret that I have is that I simulated this treatment and this treatment effects, and I can tell you that the treatment effect, the true treatment effect, is very simple. It's just 0.1, so $10 for each number of prior. So the true effect is like this, and what we estimate is like this. So you can clearly see that it underestimates the effect in this part, and it doesn't even account for the fact that it has too few observations. So that's probably not a good sign. But on the brighter side, that where you really have data, it captures the effect very well, and it doesn't lie in terms of treatment effect confidence intervals. So you should be careful with this new methodology, but you should also know that it's extremely powerful. Look at this. We did not ask this, we didn't do anything by hand to estimate at heterogeneity in treatment effects. The only thing we did, we ran the causal forest, and then we supplied some characteristics of some hypothetical people where the only difference is number of priors. And this did spectacularly well, given that we know the truth.